Okay, this is John Sullivan at Purdue University. Can people hear me?
Yep.
Yep. Okay. Let me be sure we get started. I'm going to talk about XFLR5, which we call XFLR because saying XFLR5 is just way too hard. This is a program that will predict the aerodynamic performance of wings in airplanes. It'll also do stability analysis. Some examples here on the cover page of various different types of aircraft, from simple gliders, flying wings, high-performance glider, and a parafoil. XFLR contains X-foil, and so the airfoil analysis are actually done in X-foil. The front end to doing that is a little, I find it a little easier. It's graphical to do that. The wing design is done with some lifting surface theory. There is, I put right up here at top, a series of YouTube videos on how to utilize this written. These videos are by the writer of XFLR. There's also program guides and guidelines. Did anybody have any trouble downloading and installing and getting XFLR to run? I was hoping people would have that and could follow along with what we're going to do. I think that would help you get oriented quite a bit easier. So the methodology that XFLR does, it does an inviscid wing analysis. It uses a panel method, vortex lattice method, or lifting line method. Stay away from the lifting line method for most everything that we do. Most of what you do, particularly when you've got wings and tailplanes, will be using a vortex lattice method. You're going to use the panel method for wings. Then the viscous effect are taken into account with a 2D strip analysis using XFLR. Strip analysis then is not valid for highly swept surfaces. What this means is that we get from the inviscid wing analysis, we get the section lift coefficients and the induced drag. Given the section lift coefficients and the Reynolds number, XFoil is used to calculate the viscous drag on streamlined strips. So we get the viscous drag on each of these strips. We're going to add all of those up, combine it with the induced drag to get the total drag of the wing. Now, one thing XFoil does, it does this backwards. That is, it starts out using XFoil to pre-calculate the lift and drag on the airfoil sections over an appropriate range of lift coefficients and Reynolds numbers. Now, it does this so it then has a whole matrix of lift and drag for the airfoil sections you've got, and then when it goes to the inviscid analysis, it finds the lift coefficient and Reynolds number for your strip and goes back to all the data in the first bullet and interpolates to get the viscous drag. So, and then we get the total drag. This can cause some problems, and one of the problems that I would say everybody that runs this code has, they will get an error that says point is out of the flight envelope. When this happens, what it means is that in the airfoil analysis, during the pre-calculation prior to running the inviscid analysis, the range of Reynolds numbers or the range of lift coefficients is insufficient. So for instance, we have here highly tapered wing, have a high Reynolds number here and a low Reynolds number here. We may have the same airfoil, but we've got to cover all of those Reynolds number ranges, from the Reynolds number at the chord or at the root to the Reynolds numbers at the tip. The same is true then of lift coefficients also. Okay, so what I thought I'd do is took an example of an example mission, demonstrate the characteristics of using a FLIR-1 thermal camera for detecting and geolocating fire and hot objects. Secondary was to obtain some valid design data to help, test data to help update our design tools. It's got to be capable of carrying a first or second generation FLIR with an iPhone 5 or 6. I think Team 3 was looking at a forest fire application. We've flown these FLIRs with the iPhone on a number of occasions. It's about a $100 camera. The resolution is really low, but you can clearly detect hot objects, people, and things like that with it. Not very satisfactory from a spatial resolution point of view, but for the price, it works pretty well. We're going to fly a search pattern for 20 minutes, speeds between 10 and 20 meters per second. Simple configuration, easy to build. This was something we wanted to build in a couple of days. Hand launchable. We're going to fly it with an Eagle Tree, which records data for it. And we didn't, but we wanted to ultimately do autonomous flight with a Pixhawk. So payload-wise, we've got the iPhone 6 plus the FLIR 1, a little over half a pound. Largest size is a iPhone 6 Plus with the FLIR 1. Gives us a physical size for it, which says we've got to fit that in our fuselage. We'll also put the Pixhawk in. So we're going to design for a payload of approximately 1 pound. And so conceptual design, determine initial weight, size of the UAV, did a constraint analysis. We talked about that a couple of weeks ago. I talked a little bit about the background, and Carl talked about the spreadsheets. We ran a constraint analysis. We found the wing loading was 50 newtons per square meter, and the power loading was 8 watts per newton. And then we did a weight analysis for cruise of this FLIR configuration. That gives us, from the Excel files, we put in all of this data. This is what I assume most of the teams are doing right now. We need to estimate these. And Carl gave you some ranges of parameters. The beauty is you can just go in and change those, and it immediately updates your entire design. So we're going to put those in. And out of that, we get the weights and sizes of the airplane. What we need right now are the numbers that are in yellow here. We need the wingspan, the chord, and the cruise Reynolds number. So the cruise Reynolds number is 202,000, but we want to cover this range from 10 meters per second to 20 meters per second. This was run at 15 meters per second. So corresponding Reynolds numbers are 134,000 to 269,000. So what we're going to do is run from 100,000 to missing a digit there to 300,000. And that then will cover this range so we don't get that point out of spec for the when we run the analysis. So I'm going to go ahead and we'll bring up XFLR. This is XFLR, and we're going to start. I just opened a new, this is a new file, just a new project here that you open. And the first thing we get to do is go to direct foil design. And what we're going to do here is start with an airfoil. I forgot to show that on the previous slide. We're going to start with a 2412 airfoil. And so here under foil, NACA airfoils, we can put in then the 2412, and it labels it as 2412, and there it is. We can get the width up a little bit. Sometimes, particularly when you're doing presentations using some of this, you're going to want to increase the line width and some font sizes and things of that nature. So you ought to have an airfoil now, and now we want to go and analyze the performance of that airfoil. And to do that, we go to XFoil direct analysis. So this is the menu items for doing the XFoil analysis. I'm going this up and get this over, hopefully, yeah, like that. So what we're going to do is go to analysis, and we do a batch analysis. And so this is the menu for batch analysis. And in this, we're going to put in the Reynolds number and angle of attack range that we want to cover. And that angle of attack range will correspond to a range of lift coefficients. We're going to end curved foil only. We'll do a type 1, which is a fixed speed analysis. We're going to put in a range of Reynolds numbers, 100,000. We're going to go up to 300,000. Right now we have it in increments of 10,000. We may increase that a little bit so it doesn't take quite as much time. Transition is not fixed. We'll just run alpha. We'll go alpha from -5 to 10 degrees, which will cover most everything. It won't, let me raise that a little bit to 12, and this will take us over stall a little bit. And then we go to analyze. So it's now starting to generate drag polars for all of those airfoils and all of those Reynolds numbers. So this is a NACA, standard NACA 2412, very common model airplane airfoil, 2412, 2415. So what we see then is we have drag polars, lift, drag. We see that low Reynolds numbers, 100,000, has more drag, getting to be close to twice the drag that we have at 300,000. Shape of this is pretty good. What we like, and we would get if we went to some of the Selig airfoils, or the Wortman Altice airfoils, if we get a much straighter curve, we wouldn't get so much drag up at the top. CL versus alpha, we're not quite up into the stall region. Sometimes when we move up there, it does have trouble interpolating. It'll give us an interpolation error. We probably are not going to fly up there. Maybe on landing we'll get into that configuration. And then we've got L over D here, so that, again, low Reynolds number, we're losing quite a bit of L over D relative to flying at 300,000. We're nominally somewhere in the middle of this region. Okay. We've got an airfoil now for the wing, and we'll go ahead and build a wing out of that, just the wing alone first. And so to do a wing alone, we go to wing and plane design. We're going to go to plane, and we're going to define a new wing. So we get a new menu, and the menu has a main wing, can have a biplane with a second wing, an elevator, and a fin. Right now, we're going to uncheck the elevator and fin. We're just going to run the wing to see how it works, and we need to define. So the way we define the wing is we put in sections of the wing. This is set up for symmetric mode, and we're going to put in the right side. And so we'll start at 0. The chord that we had was 202 millimeters, and it was constant chord. So both sections will be that. Our wingspan was 1.2 meters, or about 600 millimeters. All right. Now this has got some sweep in it, so we're going to take the sweep out, and then X panels are along the chord, and we probably want to increase this to about 20, and the Y panels will go up to 30. Now, if we come down here, we can, right now we're looking at surfaces. We can look at our paneling and see how it looks, see if it looks rational. You can see a few things. One, we have a cosine distribution in X, so things are packed at the leading and trailing edge. We have a sine distribution in Y, so things are packed at the tip. In the middle, the panels look to be approximately square. So this looks like a pretty good paneling for this. For vortex lattice, then we have 1,200 panels. We can go up to 6,000, 5,000 or 6,000. The same with the 3D panels. So this gives us a wing. We've got the wing defined now. Okay, and here it is. Let me turn this guy off. This is, but I made a big mistake. I got to go back. To go back, we need to go to current plane and edit it. My mistake in the wing was I didn't put the airfoils in. So right here is the airfoils. But we click on that, and it opens up. And you could have a list of 10 airfoils here to choose. We only have one at the moment, so we choose the 2412. We choose the 2412. And that now we see the 2412s here. We can, in fact, write the airfoils here. Now we can see the airfoil where before we didn't see it. So now we go back to here, here. And I knew we were in trouble because I didn't see the airfoil. So this is the surface. Again, we can look at the panels. Let me get the surfaces out of there. That's not right. We'll leave the surfaces here. Okay. So we've got the wing defined, and now we need to do an analysis of the wing. So we're going to define an analysis, which is here. We'll go with the type 1 analysis. We'll use the horseshoe vortex method, vortex lattice. Here, inertia, use the plane's inertia, that is. If you gave it a material, it would calculate the inertia over that volume. Reference dimensions, wing plan form projected on the XY plane, aero data, density, and viscosity. And you can add extra drag. So if you have a landing gear that you can't get in here, you could add the drag for that. So this is okay. And then we come over to analysis here. We're going to run a sequence. We're going to run -5 to 10 degrees. And then be sure store op point is set, and we'll go to analyze. So it's going to come in and calculate this over a range of angles of attack that we put in. Okay, now you can see we have the case we just ran. I ran this at 10 meters per second. Let me go back and show you. That was here. I put in 10 meters per second. I thought to show you there was 10 meters per second in there. So this was our low Reynolds number case. We don't want to do anything more with that. And this is the angle of attack that we're at. We can now go ahead and look at the pressure distribution. Surfaces are turned off. So this is then the pressure distribution that we have. We might come up to a little higher angle of attack here. At the moment, we have a problem. This is a common thing also. The CP, of course, positive CP can't go over 1. And what it has in common for vortex lattice, sometimes in the corners, we get a 1-point glitch, which reset these scales. So we have to go in and reset the 3D scales. We're going to automatically go out of auto. We're going to set this to 1, and we'll set this to -3. Apply, and now we can see the pressure distribution on the wing. Okay, so as you expect, higher pressure here going off, and as you can see, as we come out to the tip, of course, the lift is going off, and that's what the pressure distribution also shows. In the right and left-hand corner, there's a lot of information available. Right-hand corner, velocity alpha, we had a side slip. CL for this case at 5 degrees is 0.5. Efficiency 0.99. LRD is 18, drag is 0.28. The moment coefficients, center of pressure is at 68 millimeters. That's 68 millimeters back from the leading edge, back about here. At the moment, we have the CG at 0, which is at the center of the wing, at the leading edge. On the other side, we have all the dimensions that we put in. It'll always calculate the mean aerodynamic center. Trivial for this case, we've got an aspect ratio of almost 6. Notice it also calculates the neutral point for you. So this is, as Professor Kahn talked about, this is the location of the neutral point. Okay. So then we can look over at the performance. This is the wing performance now. We have the drag polar for this finite wing, which is, of course, last. We have the lift coefficient versus alpha. We have the moment coefficient versus alpha. I'm going to change that to be the moment coefficient versus lift coefficient. And I put the wrong axis on. So I want this guy to be CM as the y-axis. CL. Okay. So this is a normal way, there's several reasons to do CL versus alpha. But what we can see, and you'll notice from, remember from Dr. Kahn's lecture, this is an unstable airplane. I believe it's not. So we don't have a tail on it. So we're clearly going to have to do some more for that. All right. We can further go here, and we can look at the span-wise lift coefficient for this wing. This is important for you to use in your structural analysis. So this gives you the load distribution. You can go ahead and right-click in here, and for the current polar, you can export the results. It'll take all these results and put it in a text file. So you can take that text file and put it into whatever structural analysis you're using to get the right load distribution. Okay. Let's take a look back here. We can also go and take a look at the streamlines. For this case, we can always go and rotate everything around to look at it any way we want to. There's set lines you can see here. You can see the roll-up, the tip vortices. You can see the decrease of the wake in the middle of the wing. This has an effect, of course, on your tail. We'll put it in there. Got it from the side, top view, and back to the so it does give you some wake deflection. It does give you a little bit of a roll-up. I wouldn't put a lot of stock into the exact details of the roll-up, but that, in fact, is the way this looks. I'm going to stop there and ask everybody with questions, things not working. What do you need to do?
Which option did you select to get the vortices to show?
Okay, the question is, how did I get the wake to show? To get the wake to show, go over to Stream. Here on the right-hand side, there's a button that says Stream, and click that. So if I unclick it, they'll go away, and I click it, they'll come back. Okay.
Hey, I have a question here.
Sure.
A couple of us are having a problem that when we try to open it, it can't find a .dil file.
Yeah.
And then it
.dil.
tells it to reinstall.
Okay. Well, that's why I asked, first of all, who had trouble getting it to run. And so on SharePoint, here's the problem. These files come in Microsoft C++, and some computers have installed and some don't. And it seems to me it's about 50-50. So on the SharePoint, both Carl and I, in today's lab, underneath that, you will find an XFLR folder. In the XFLR folder, you will find two zip files for the two DLL files that you need. The two DLL files go this is the folder with all your files in it, and here is the runtime DLL, and here's this MSBCP file. So put them in this directory, which is the directory with XFLR and just unzip them, and that should make it work. Well, try that while I continue. Is there some other questions? Okay. In the appendix of the PowerPoint are step-by-step with screenshots of some of this. So that should in fact help you out. All right. What I want to do now is go and look at the tail. Oops, we're going to get to it here. And so Professor Kahn used some historical data for parameters relative to stability. We're going to use a static margin. In our case, we use 10%. We're going to use a tail volume. In our case, we'll use 0.5 based on, again, historical data. This is for the horizontal tail. For the vertical tail, we'll use a tail volume of 0.25. Again, sort of the median of the historical values for that. One of the things that that's really useful I found is this proportions of RC aircraft. This diagram goes back some number of decades, but what it does is that for a typical model airplane, what are the sizes of things? It's not a bad place to start. Particularly, you might not know, what's the distance between, the leading edge of the quarter cord of the wing to the quarter cord of the tail, and what are some of the typical sizes for everything. This isn't the end, but you can put this in and it'll get you started, and then you're going to find out, well, it's not the stability you want, it doesn't perform the way you want, but you'll have something that you can begin to change. Professor Kahn also had a way to get the aerodynamic center, the neutral point. We're going to get these directly out of XFLR, but this is a way very similar to the one that he had. And we used it for this. So then, using those, we get horizontal tail sitting back half a meter, 4/10 of a meter span, 1/10 of a meter in chord, vertical tail, also back the same distance. We're both going to have a 006 airfoil, typical for this. And then what we need is to calculate the range of Reynolds numbers. So the horizontal tail, 10 meters per second, we're running 74,000 up to 148,000. For the vertical, out at the tip, we're running 44,000 up to 89,000. So now we'll put the tail in. So what we want to do now is go to plane, and we're going to just take this wing and we're going to edit it. And what we're going to do now is turn on the elevator and turn on the fin, and then we can go in and define those two. So it always comes up with something for you to start with. For the horizontal, excuse me, horizontal tail, we had a chord of 0.111, and it was constant. We had a span of 0.44, so a half span of 0.22. We had no offset. And again, X panels, X panels we might go up to say a dozen, and here we probably want to go up to about 20 panels. Not seeing. We also need to go here and set the offset, or the distance back, and we had it set at 500 millimeters aft of that. Okay. And I'm having, there it is. I wonder why it wasn't showing up. Now, again, it's looking pretty good. We didn't put the foils in, but now we're going to put the foils I didn't analyze yet in. So I'm going to have to go back and back to X-foil and analyze the foil. So we've got our 2412. We now need to add a 006 airfoil, 0006 rather, airfoil. And there it is. Doing one. Okay, there's our symmetrical 006 airfoil for the family. We need then to go ahead and do the X-foil direct analysis again, and it'll put that data right on here. So we go to analysis, batch. Now we're going to go from Reynolds number of 40,000 up to a Reynolds number of 160,000. 160,000. We can keep the 20 increment of 20 here. I'm going to just run this for 0 to 5 degrees angle of attack. The 006 at these Reynolds number will start stalling somewhere just a little bit above 5 degrees and give us some difficulty. So we go to analyze, and here now comes the 006. And what you can see is it has a bad data point here. And if we went up even further, we'd start picking up more bad data points. Well, let's see. This may give us an out of, or not able to interpolate error. If it does, we'll have to come back and redo this. So now, we've run both airfoils. We have the data for both airfoils. We come back to our plane and wing design. Here, we come back to plane, edit. It lost what we put in, so because I didn't change the name, this was set back 500. We have to define the elevator. This was 0.11 or 111, constant 111. The span of the horizontal tail was 0.44, so half span is 0.222. We've got no offset. That offset would give a sweep. We need to put a 006 airfoil in there and a 006 airfoil in there. And for some reason the display is not doing what I want at the moment. 12 and about 20.
Another question for you.
Yes.
Do I have to be in millimeters?
No.
Or
Well, you
meters?
could change to a British system. It can be in meters, millimeters, inches, or feet.
Because you're putting it in at 0.22 millimeters right now.
You
That's
probably
fine.
want it at 20.
Well, thank you very much. I was wondering why the span was so damn short. That's looking an awful lot better, isn't it? Thanks. I need all the help I can get here. Okay, and the paneling looks pretty good for a horizontal. Okay. But as I said, you can choose your units as an options button up here in the options, and you can choose your units to whatever. And then this guy is also out at, one of my problems is I had it in millimeters yesterday, and today for some reason I'm in meters, or in millimeters rather than meters. Okay. So we define it, and 0 chord was again 0.1.1. I made it tapered. I'll do it again, 1.1. And the tip chord I have at 67 millimeters, and the span of the tip is 0.2. 200. Okay, pretty light on the paneling, so we'll kick both of these up to about 15 and 15. Kicking up the paneling gives you a little more accuracy, and you know we've got plenty of panels, so we don't have to worry too much about that. Okay, so we've got these defined. We've got these defined. We're going to save this as a new file, and this is we'll call wing and tail. So we don't lose the other data that we've generated. Okay, so now we have an airplane with a wing and tail. We need to go just as do exactly what we did before. We need to do analysis. We've got to define an analysis. We've been running at 10 meters per second, fixed speed, the analysis, horseshoe vortices, inertia, use the airplane's inertia that's in there, same reference dimension, same arrow table. Okay, so that is then the wing, and we're going to run it, the same case, -5 to 10 degrees. It's giving me, now I've got a long and tail, so that's nice, and it's not finding the, so we need to go back and do current plane, edit, main wing. So we got it here. Exactly as we had before. Oh, for the fin, I'm sorry. I did not define it for the fin. I did define it for the wing. So when I did the fin, I didn't put that in. So that is the problem. We need to go back over the fin. And here, I need to put in the 006. Find analysis. Okay. This is a good place to, sometimes we want to change the name of the polar. For instance, if we're moving the CG around, we would put the CG location here, and we'll do that. But right now, it wasn't working, so we'll just overwrite it, and now we'll go ahead and analyze. Okay, so here's our airplane. Get it up to maybe 5 degrees angle of attack here. Half pressure distribution looks right. We can turn on the streamlines and take a look at them. They will be influenced by the tail. We've got the streamlines coming off the tail. Also, right now we're running a lift coefficient of 0.5, drag of 0.03. We have, go and take a look now. Wing and tail, we're getting closer to something that might be stable, but we'd have to be flying at a CL of 0.05, which probably is too low for you. But if we could shift this curve over, keeping that slope, we'd be okay. We've got two ways to move the curve around. One, we can move the CG, which is what we will do first, and the other one is to reset the elevator angle. And then from a load distribution, this is the wing and this is the tail. Didn't have quite enough points in there, but what we can see is this tail is lifting upwards quite heavily, and so we would probably want to put a little negative angle of attack on the tail, or put an elevator deflection there to take care of that. So what we can do now is we have right now, we have the CG at 0. The neutral point is here at 90. For instance, let's go in and put the CG at the neutral point. What are we going to expect when the CG is at the neutral point? What would this curve look like if I put the CG at the neutral point? Horst? Anybody else? What's going to happen to the CMCL or CM alpha curve when we're at the neutral point?
What is that right now?
What's that?
What's that right now?
This is
No, I'm not going to see
0.
The CG said
It's at the leading edge.
it tends to nose up.
Okay. So I'm asking, what would this is the curve we've got, the blue one. What's it going to look like?
I believe it was horizontal.
It'll be horizontal. Exactly right. Well, let's go see it if indeed it is horizontal. And to do that, we go back into plane, current plane, edit. And I'm sorry, wrong menu. I need to go into analysis, define analysis, and define inertia. And rather than doing the plane inertia, and I'll show you some other ways we can put in lots of things here, but we're going to put XCG then at, where was it, like 90 millimeters? I forgot exactly. Somebody tell me on the other graph. Bring the plane up and tell me what X neutral was. 90 millimeters. Yes, no? Nobody knows? Nobody can read it? Okay, we'll leave it at 90 and see. That's pretty close, I think, to where I think it may have been 96. Try 96. Okay, so we'll put that in there. Now, we are going to, we said analysis with, this was 96. We're okay here. What we want to do is change this and put down here CG 0.9. Well, actually, it's not 0.9, it's 96 millimeters. So we can distinguish it from the others. Okay.
So do we edit the mass?
Edit which?
The mass, the plane mass. Does it affect anything?
I don't know. I still don't know what you said.
The plane mass, the weight of the plane.
No, we haven't changed that. We're just moving the CG around. Okay. So now we're ready to go. We can analyze it. Okay. Well, 9.6 was too much, and so what I was trying to remember was this number over here, which was 90, not 96. So what we've got is not just a neutral airplane, but an unstable airplane. If I put 90 in there, it'll be a horizontal. Let's do one more. And what we want to do is put the CG somewhere in between, back maybe at point or 80, sort of 80 millimeters, and see what that does. So current plane, analyze, edit, and we do, I'm sorry, we don't want this right now. We want the analysis, define analysis for the inertia. We're going to put this guy at 80 millimeters, and let's see what we get here. I want to change this guy, take it out of auto, and put CG 80. Okay. And analyze. Okay, so now for CG is 80, we've got the yellow curve. It's shallower than the blue curve. That's looking good, but it's too low. We want to raise it up. And to raise it up, this is how you trim your airplane with your elevator. You can have a series of lines that all be parallel to the yellow line for different angles of attack of your elevator or different elevator setting angles. Right now, we will go ahead and just change. This would be like a floating horizontal surface. There's no elevator. It's just a solid surface. But we're going to change the angle of it here. So we'll go down to a minus 0.5, a half a degree, about 0.5. 0.5. 0.5 degrees angle, and this will. Okay, we're going to save as new, and this is going to be horizontal tail. Horizontal tail minus 0.5 degrees. And now, fine analysis always. This is the same 10 meters per second inertia. We've got the CG at 80, so we run this. This green line is now there. What we probably ought to do is go in and the current graph, we define graph settings. Let's change the axis, change the scale. We want to change the scale. The y-axis, we don't have to go. We don't want to go more than minus 0.1. And probably put one here. Okay, so now we can begin to see that we have a stable airplane. Its trim point is at CL of about 0.35, which was very close to the design point we chose. We could estimate the stability margin for this. The stability margin, as Professor Kahn said, is just DCM DCL. So DCM is just this value here from 0 to here, and DCL is from 0 to here. So it's simply this value over this value, and that'll give you a static margin of about 7%. So you've got everything here, longitudinal stability. You can move it around quite easily. Okay. I have one more thing to show you. I'm going to bring up a new program, but I want to stop. Clearly, I've gone pretty quick to do this. Okay, we'll go ahead and see what Professor Kahn showed you was the static stability. We have two types of static and dynamic stability. We looked at this and looked here at the trim point, negative slope. Dynamic stability, we get some oscillations. They damp out, we're stable. We don't. We get 6 modes. There's 2 longitudinal, 2 short period modes. Lateral, we get spiral mode, a roll damping mode, and a Dutch roll mode. That's 8 modes. Okay. So I'm going to bring up a different program. I'm not going to go through, just show you some results from that. And this is an example that, and all of these example files are on SharePoint. So, like other computer programs, start with something that's there and modify it, because it works. Well, sometimes when I push the right button, it works. And when you modify it, it doesn't work. You can always go back to something that does work. There is a detail example up here also. So we're going to do that. We're not going to save that. Okay, so this is a glider, really high performance type of glider, and looks a lot like what we just did, but it's got polyhedral, tails offset a little bit. But what you can do is go ahead and put in point masses. You can put in distributed masses. You can calculate if this were all foam wing or foam fiberglass wing, it will calculate the moment of inertia and location of the CG of the wing. But in this case, typical model airplane, in a glider, depending on what contest you're in, you may need some nose weight, fuselage, battery and receiver, and then the wings, and then you have your servos out. So you've got all of the masses in there that you need. So this will then calculate the dynamic stability. I have a case here that's for a static margin of 15%. That's the case here. This new menu comes up, and what it does is lets you take a look at the note. It gives you all the data too, and it's written out to a log file, but this allows you to take a look. So this is longitudinal mode 1. It's a highly damped mode, and this is the initial condition. We put a perturbation into it. Of course, we magnified it a lot so you can see it, and then what that does is it goes down. There's a little undershoot, and it comes right back up. But it's pretty. And there's 2 of those modes. They're symmetric pair of modes. there. And then in the longitudinal mode, we've got the fugoid motion. And this is a fugoid motion in the coordinate systems of the airplane. This is the one when you throw your glider here later in the semester, you will see it, wander up and down until you get the CG in the right place. This gives you some of the characteristics of that, the natural frequency and the damping coefficient, other parameters. All the inertias are contained in a log file, which is up here. We can do the same thing in the lateral modes. This is the Dutch roll mode. This is like that was just a simple roll mode, highly damped, didn't undershoot at all. Dutch roll is a pair of Dutch roll modes, symmetric Dutch roll modes. And then there's the spiral instability. This is playing. It is a spiral instability. What it's doing is just moving. It's very, very slow. You will have this in your airplane. Pilot automatically corrects for this. It is a killer of people like the Kennedys. Got in a spiral mode because they were in a very low visibility situation. So this is here. You can get the full static and dynamic characteristics if you want. I think the main thing you get out of XFlyer is good drag because it's using XFoil for the viscous drag. Other programs are going to use some of their approximation. This lets you put your airfoil coordinates in and get those out. So in the appendix, I have step-by-step instructions for all of this. You can put in airfoil coordinates. There's a set of airfoil coordinates for the 66, 2215, a 15% laminar flow, airflow. You have to put the coordinates in XY coordinates. You start at the trailing edge. In this case, we went over the upper surface to the nose and back down the lower surface. You can go the other way. But you always start at the trailing edge. Make sure you don't have any double points. Double points will mess up XFlyer. Then out of that, this case, that happens to be a laminar flow airfoil. So we get this big, nice drag bucket associated with it. But that's happening at a Reynolds number of 2 million, a little higher than you're going to be at. But a very common early laminar flow is laminar flow because the pressure gradient is slightly favorable over most of this. Transition occurs at 0.746 or somewhere around here on that. Okay, I'm done. Any questions?
Hey, Dr. Sullivan, this is Steve at BYU. I just had a general question for students. I don't know if you or Carl have already gone over this, but can you give the University of Illinois website, has hundreds of airfoils. Have we given some kind of general families that students should look at or appropriate places to start? And because they're going to use XFlyer to start designing their wings and things like that.
Yeah. I think in my notes in the appendix, I have a link to the UIUC database. I thought that was here maybe. Yeah, it's right here. Got hundreds of airfoils. What we're looking for are generally pretty good low Reynolds number airfoils. Selig airfoils, lots of people use for lots of things. Drella airfoils, another good set of low-speed airfoils. Martin Epperle, I'm not sure I'm pronouncing his name properly. German has the MH airfoils, a bunch of those. Some of the Wortmann airfoils are good at, although they were designed for high Reynolds numbers, they're good at low Reynolds numbers. You have to be careful. actually be careful with a lot of things off of the UIUC website. Some of the data is a little bumpy, and so you have to go into XFoil and do a smoothing operation on that. So you want something. Your airplanes, for the most part, are going to be cruising at Reynolds number at order 2,000 or 200,000, which is very low. But there's quite a few airfoils that perform well there, and perform well, from lift coefficients of say minus 0.2 up to 1.2 or so. There's a couple of Selegs that have a tremendous amount of camber in them. That also will work up to a CL of 1.5. The problem is they're going to start to stall on the lower surface at maybe a CL of 0.5, which may not work for your airplane.
Right, yeah, we can go through and look at some example ones and show kind of what the coordinates look like. I was going to include some of that in part of my demonstration.
Right. Okay, anything else for me? I want to get on to Carl.
So it's going to be intimidating right now.